Morena everyone. This is the first of 3 videos where I'm going to step through the derived grade exams for level 3 chemistry in 2022 at TGC. You will have the marking schedule available, so you're not going to have perfect answers written here. You will need to have a look at that schedule as well. I'll try and give you a few tips and hints, things to look for to help you improve your grade or your learning, whatever you need to do. So starting off at question 1, these are our electron configurations. I've just jotted down the general order there. You do need to know this general order. There's a couple of ways you can kind of help yourself remember this. If you need to go through those with me, let me know. Cl is number 18 on the periodic table, sorry, number 17, but it's got an extra electron making it 18. So we're going to go 2, 2s2 is 4, 2p6 is 10, 3s2 is 12, 3p6 makes 18. And obviously remembering that we are kind of looking for ions to get a reasonably full outer shell in many cases. Let's do titanium next. I think it's number 22. So we're going to go 1s2, 2s2, 2p6, 3s2, 3p6. So that takes us to 18. The next two, remember we skipped to 4s2, so that's 20. And then we go back to 3d and make the shell up to 22. A lot of people got this one wrong. You've forgotten the trick here. So chromium is, it's actually an exception, I think. It's, where's my periodic table? Must be number 24. I'm just going to check that on my periodic table. So what we need to do with a positive ion, number 24, is we need to write the atom first. So I'm going to write out 24 for chromium. Okay, now chromium's a tricky one. 3s2, 3p6, 4s2, 3d4. So when we look at chromium, we have to remember it's one of our exceptions, and chromium is more stable if we have 1 4s electron and 5 3d electrons. So 2 half full orbitals there, subshells. So if we now look at the 3+, that means we lose 3 electrons. So we're going to lose the entire 4s shell, and we're going to lose 2 of those ending in 3d3. Right, so that's the answer for that one there, and you had to get 2 of those correct for an achieved. I really encourage you to work on your Lewis diagrams. They should be easy marks for you. So Cl in the middle, 3 Fs evenly spread around the outside. Start from the outside because any weird stuff goes on in the middle. So any halogen, 2, 4, 6 and 1 from the Cl, 2, 4, 6 and 1 from the Cl, 2, 4, 6, 7 and 1 from the Cl. Right, so now all of my Fs have got their 7 plus 1 from the Cl they're bonded to. Now that Cl, we just have to make sure that's right. It has 7 valence electrons as well. It's also a halogen. We've only used 3, so I'm going to put 2 more pairs of electrons, making sure they're not anywhere near my other ones. Now I've done that with dots and crosses, but actually the way that I'd prefer you to do that is to replace the bonds. You just do have to do this carefully with a line. You do need to make sure you don't override your dots and crosses with a line. They have to be clearly rubbed out. Right, so this one I'm just going to do I in the middle and 4 Cls evenly placed, and I'm going to put my single bonds in to start with. Halogens always make single bonds. We don't even have to really think about that. And the outer ones always end up with their 8 electrons. Okay, so I'm going to do that. All right, and then I just need to check the central atom. I've used 4 from the iodine. We know it's got 7, 5, 6, 7, and we've got 1 extra there. The charge means we do have to show that we've got an extra electron from somewhere else. This is 5 areas of electron density with 3 bonded. That's going to be a T shape. And this is 6 areas of electron density with 2 non-bonded. That's going to be a square planar. That's a very easy merit question if you can just work on those shapes and names. Okay, so now we're up to our periodic trend question. So we're looking in this question at the radius. So that's the distance from the middle of the nucleus to the outermost electron. We've been given the answers, we just need to explain them. Too many people here told me that Cl and Cl minus are in the same group or the same period. They are the same atom, right? They're the same element. You can't be in the same period, like if you're the same element, you're in the same box. So in this one, again, it's protons and shells. Both have 17 protons, as both are chlorine. Cl minus is going to be Cl is going to be 287, and Cl minus is going to be 288. Right, so I can do the simple electron configuration here, and it's going to give me the answers. So I'm going to write that both have 17 protons, so the same nuclear charge. Both have 3 shells, so therefore the same amount of shielding. So please remember that shielding comes from the number of shells. Some of you were a little bit confused about that. If you do use that phrase shielding, can you please clarify that as it is inner shell electron repulsions. So what's the difference? The difference is this valence shell here. So the Cl minus has 8 electrons in the valence shell compared to the Cl having 7. 8 electrons in valence shell repel more than 7 electrons in the valence shell. And that's it. So if you've got all that information there written in a couple of nice sentences, some of you resorted to nonsense. I appreciate that you tried, but please don't talk about protons being in the outer shell, and please don't talk about protons and electrons repelling. Opposite charges attract, like charges repel. That's just basic, and you need to know that. Over on this one, we've got ionization energy. So we need to define ionization energy. So that's the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. These words are important. You cannot substitute atoms for substance or molecule or anything else, and it is important that it's gaseous. Right, so I'm going to look up here and I'm going to write my protons in shells. 9 protons, 15 protons, 17 protons, 2 shells, 3 shells, 3 shells. Okay, I'm going to look for some relationships in here. These two are in the same group. They're both halogens, so I'm going to compare those. And these two are in the same period. So the easiest way to answer this question is to compare these two and then compare these two. All right, so then you get the group comparison and the period comparison. So the group comparison, right, so the idea about these two here, even though this has got more protons and so it has got a stronger nuclear charge, chlorine also has more shells. So that accounts for its lower ionization energy than fluorine, right? You do need to have that despite having more protons. Chlorine also has more shells. So we can equate more shells to more shielding. So despite, some of you didn't get this bit, more protons, Cl has 3 shells compared to F's 2. 3 shells has more shielding and outer electron further from nucleus. Okay, so that these ideas reduces the attraction between the nucleus and the valence electron. And this decreases the first ionization energy. Okay, when we're looking across a period, the key ideas are, so we're looking at these two here, right? We're looking at these two comparisons. Both have the same number of shells and therefore shielding and general distance. However, your chlorine has got a stronger nuclear charge than your phosphorus, so chlorine is going to have a greater attraction between its nucleus and its valence electrons. Right, so it is actually quite simple. It doesn't matter what they pick, And it doesn't matter if it's ionization energy or atomic radius or electronegativity. The ideas for the explanation are the same. Okay, so period is same shells and shielding. But more protons in Cl than P. So Cl, try not to use it, has stronger nuclear charge and a greater attraction for those valence electrons. I'm not going to write too much more, or this video is going to take forever. Okay, question 2. Oh no, still on question 1. Okay, so this one here is our polarity question. If you get this, you should nail it, because it really is the same idea as level 2. So we've got to compare and contrast. A few of us forgot to do that. So what I would do is I would start with SF4 and I would explain its shape. So I'm going to start with 5 areas of electron density around the central atom. I'm going to say that they occupy positions to minimize repulsion. So I'm actually doing the shape and the polarity in this. One area is non-bonded, and so the molecular shape is seesaw. Okay, I'm then going to say there are 4 polar bonds, as F is more electronegative than S. Okay, and I'm going to say because the shape is seesaw, the dipoles formed by these polar bonds are arranged. Let's talk about how the dipoles are arranged asymmetrically. Therefore, don't cancel, and therefore SF4 is polar. Okay, so I've got the shapes, I've got the areas of electron density total, the repulsion idea for the parent shape. You don't generally need to do the bond angle at level 3, but those of you who did, that's fine. And then you're talking about each polar bond and if the shape means that those dipoles are arranged symmetrically or asymmetrically. Same for the trigonal bipyramid here. So we've got 5 areas of electron density again around that central atom. So the parent shape will be the same of trigonal bipyramid. However, because all 5 are bonded, this molecular shape changes. All right, so that's one difference there. So we've got to compare and contrast. Both have 5 areas of electron density. This one has a non-bonded, this one has no non-bonding. The other difference with this one is that we have 2 types of dipole, and you need to be clear about that. So with the dipoles here, or the polar bonds, so we've got polar bonds, we've got Cl is more electronegative than P, and we've got F is more electronegative than P. Okay, so there are 2 types of polar bond. We're going to say this slightly differently. We're going to say that this trigonal bipyramid means that the polar bonds are arranged symmetrically, but we're going to say because, sorry, I'm trying to get this right for you, because there are 2 different dipoles, their effects do not cancel. And this is also polar. Okay, so slightly different explanation. Go back to the marking schedule if you need a bit more detail, but do try and write a compare and contrast statement of some description. So you've got a couple of things. You've got same areas of electron density, so same parent shapes, same bond angle, one non-bonding, which means these dipoles are arranged asymmetrically, different dipoles, which means the dipoles don't cancel. That's the main idea there. Okay, question 2. This was a little bit appalling, to be perfectly honest. So this is your basic thermochemistry, right? So we've got up here a liquid. So liquids are kind of arranged like that, their particles, going to a gas, right? So what we are doing is we are breaking all of the bonds between those particles. And breaking bonds requires energy, and so that's an endothermic process. What's the reason? energy is absorbed to break the bonds between the liquid to turn the liquid into a gas. Breaking bonds and absorbing energy is an endothermic process. This one here was really nasty, actually. It was a really, really tricky Hess's law question. So there were a couple of ways to do this. I actually ended up multiplying this to give 3 of everything. So I left that as 3 of those, although I reversed that. And then I multiplied that one by 2 to cancel out those. And then I multiplied that one by 2 to get 2 of those. And I left that one how it was. And then when I got my answer, I divided by 3. However, most of you didn't do that. So most of you who did it reversed that one and you multiplied it by 2/3. This is actually quite a tricky way to do it, I reckon. You then divided this one by 3. Oh, sorry, by 2/3. Oh, sorry, that one was a 2/3. You didn't reverse this, but you multiplied it by 2/3. This one you also multiplied by 2/3, and this one you multiplied by 1/3. Now, if you did all that, that cancelled out. So there were kind of 2 ways to do that. My suggestion is that you have a look at the marking schedule, but if you want to go through my way, which I personally found easier, I'm happy to show you. So that's answer was minus 1025 kilojoules per mole. I honestly don't think you'll get one that hard in the real exam. That was quite a tricky one. This one was also quite a tricky one, not quite so tricky. One of the things that I noticed was that people really need to think about what these are and how we use them. So this is a volume, but we do need to divide it by 1,000 to put it into litres. That's a concentration. And that's the same volume and the same concentration. Now, many of you worked out the number of moles by going N equals CV, and most of you got that right, 0.15 times 0.75, and that gave you 0.1125 moles, and then too many of you added the 2 moles together. So just remember, if you've got, we've got HCl plus NaOH going to NaCl plus H2O. Okay, I have 1 mole of that reacting with 1 mole of that to give me 1 mole of that and 1 mole of that. I don't have 1 mole plus 1 mole making 2 moles. So I still have 1 mole reacting and 1 mole reacting. So that needed to stay as it was. I then have, they've given us the combined mass, got the assumed heat capacity of a solution, and we've got the energy released. Okay, so the idea there is that we know from this equation here that if we have 1 mole of either of these, we release 58 kilojoules. So if we have 0.1125, it's going to be a whole lot, about 1/10 of that, times 58, and that equals 6.525 kilojoules of energy released. So that's actually just thinking about what the question is asking you, right? And this is actually a working backward question, which is why it's quite hard. We do need to go down to the next one, so that could be a correct answer there. And then we need to carry on and calculate the temperature change. So at this stage, we're going to use Q equals MC delta T. The Q comes from there, from that answer up there. The mass is our total mass up here, which is 300 grams. And we know the C, which is 4.18. So we can work out the delta T. The only thing is, take a good look at these units here. When you're using Q equals MC delta T, you need joules, you need grams. So some of you changed the grams into kilograms and didn't change the kilojoules to joules. Just use this number to help you remember what the units are. So what we needed there was 6.525 times 1,000. That turns that into joules, equals 300 grams times 4.18 times X, and that's going to be our change in temperature. So if we rearrange and solve for X, that is going to give us 5.20 degrees Celsius. And that is going to be a temperature rise because that's an exothermic reaction. That's a delta H negative. Okay, so that was a bit of a tricky one, but quite a few of you got that, so good job if you got that. Right, question 3. This was fascinating. We had 2 alcohols here in this table with our width. Alcohol, if they've got the same functional group, they're going to have the same attractive forces. I'm going to abbreviate, but you're not going to abbreviate unless you write it out in full first. And I was pretty hard on this because you need to know you cannot just abbreviate in your exam. So this one has got hydrogen bonds because it's got an O bonded to an H. It's polar, so it's got PD, and it's got TD. Right, so I'm abbreviating. You would write this out in full, except you can write H bonds, and then you would write your abbreviation next to it, and now you can continue to use that abbreviation. This does have an electronegative oxygen, so it's polar, and it also forms TD, and this is the same as this. These are both alcohols, right? H bond, PD, TD. Okay, if you don't get these right, you are not going to get the next bits right. This is one that we can really make some important gains in, so do work on this. Right, so now we're looking at ethanol and propan-2-ol. So we would start by saying that both of these form the same 3 types of width, and I would expect you to explain why. So hydrogen bonds because they both contain an oxygen covalently bonded to hydrogen. PD because both of them are polar, and TD because all molecules form TD. One really important thing that many of you did not state is that these weak intermolecular forces are between molecules. You really have to do this. If I can't tell that you know that in your answer, you're going to limit your grade to an A or an M, depending on how generous your marker is feeling. So if these two have the same types of weak intermolecular force, why is this one got such a higher enthalpy of vaporization than this one? And the answer lies in the molar mass. So we needed to use the molar mass here. So this one has got a larger molar mass than this one. You can actually calculate it and use it. So that's 46, 12 plus 12 plus 16 plus 6. This one here would be 36 for the 3 carbons, 16 for the oxygen, and 3, 6, 7, 8. So that's 20, 3, 4, 5. So that is 60. Right, so that's 60 grams per mole, and that's 46. So that is a significant difference. Some of you wanted to talk about how linear these two are. And you're right, this one is more linear than this. But if that was the factor that was important, then this one should have a higher enthalpy of vaporization than this, because linear would get things closer. So in this one, you really wanted to say molar mass is higher in propan-2-ol, and this means there's a larger electron cloud. This is an important statement in linking, and therefore stronger TD. Please note that the molar mass does not affect the permanent dipole strength or the hydrogen bond strength, just the TD strength. Okay, and then we had to do the same question, but we were comparing propanone and propan-2-ol. So we come back over here and we look at propanone and propan-2-ol, and the obvious difference is this one forms 3 types of force and this one forms 2. We need to compare the molar mass, right? So we always compare the molar mass. These two have a very similar molar mass. It's only 1 or 2 units different. So the bottom one's 60. This one is 36 plus 16 is 40, 52 is 58. Okay, so please don't think that a difference in molar mass of 2 is important, but we need to say these are essentially similar. So similar molar masses. So similar TD. That's an important statement, because if we didn't check that, then we might have a TD difference that might account for the change. But 3 types of width compared to only 2 types of width. And because they've got a similar TD, we can really say that the hydrogen bond makes a difference there. Hardly anyone got this right. So enthalpy of formation is the formation of 1 mole of this substance from its elements in their standard states. K, a metal, chlorine, a gas, oxygen, a gas. So that's how you do that one there. This one here, all of our data is an enthalpy of formation, so we can do products minus reactants here. Big error that I saw a number of times, these are the products, these are the reactants. So many of you wrote this, but then did reactants minus products. So you're going to get no marks for that. You do need to know that these are the products and these are the reactants. Other error is that people couldn't figure out what to do with magnesium. Elements have an enthalpy of formation of 0, and that's something you do need to know. Okay, so the answer for that one was -1852. If you did reactants minus products, you would have got +1852, and you would have got nothing for it because you would have got everything the wrong way round. So please make sure you get the products and the reactants right. This was a lovely entropy question for the last question in the paper. So it's our entropy changes. So we wanted to be very clear. We're talking about entropy of the system. So we've got, on the left-hand side, we've got 2, 4, 5 moles, and we've got solid and aqueous. On the right side, we've got only, on the left side, we've got 3 moles. I missed that. On the right side, we've got 4. So we've got 3 going to 4. We've got a solid on the left and no solid on the right. So we are increasing the entropy of the system. Entropy of the system as we are getting more moles and our states are more disordered. So total, we get more disorder here. And we're talking about the dispersal of matter is increasing, or the randomness and disorder. Okay, is increasing. With regards to the entropy of the surroundings, we've got an exothermic reaction. So we need to say delta H negative, therefore exo, therefore heat is released, which increases the entropy of the surroundings. And that's by making the surrounding particles move faster. That'll be your air or your water, and that's going to increase disorder in those particles. Finally, you want to put it together saying the total entropy is a combination of the entropy of the system and the entropy of the surroundings. If this one is positive and this one is positive, the total will be positive, and that will mean that we have a total increasing entropy and a spontaneous reaction. Boom, work on it. Right, great job, team. I hope you're having a great holiday, and I will see you soon. Or you might not be on holiday yet. I hope you do have a great holiday. Ka kite.